Okay, hello everyone. Okay, we are considering the elementary row operations and stuff. Let me review what we considered the other day briefly and then go to the next part. So here is what we considered. So we considered the elementary row operations, which consists of three steps. One is the interchanging the order of any two equations in the system. And second one is the scaling, which multiplies any equation in the system by some non-zero constant. And replacement adds a constant multiple of any equation to another equation in the system. And as I mentioned at the bottom, these operations are reversible, which means we can undo those operations. Okay. Then we can, given a system of equations, we want to perform these elementary row operations to derive a simpler version which has the same solution set. And in the example we considered, we given a system of equations, we constructed one augmented matrix which is in rectangular form with with many non-zero values in certain in not the rectangular matrix. But we perform this sequence of elementary row operations to transform the matrix into the following a matrix with the following properties. First, the first non-zero coefficient in each equation is 1. And then if an unknown is the first unknown with a non-zero coefficient in some equation, then that unknown appears only in that specific equation. In other words, that unknown does not occur in the other equations, which means so that unknown occurs with a zero coefficient in each of the other equations, right? So So in this box below, if A1 appears with non-zero coefficient 1, and if that's the first unknown in the first equation, then that A1 appears only in the first equation, not in the second or third equation. And in the second equation, A3 is the first non-zero unknown. That's the unknown with non-zero coefficient. Okay, A3 is the first unknown with non-zero constant, the coefficient. Then A3 appears with the zero coefficient in the first or third equation, right? Because in the first equation we have 0 times A3, and in the third equation we also have 0 times A3. So that they just disappear because those two terms have zero coefficients. In a similar way, A4 is the unknown, the first unknown with the non-zero coefficient. So A4 appears only in the third equation, not in the first or second equation. And then we have the following property. The third one, I told you to read this, okay? So the first unknown with a non-zero coefficient in any equation has a larger subscript than first unknown with a non-zero coefficient in any preceding equation. So what is the subscript of A1 in the first equation? 1. And what is the subscript of the first unknown in the second equation? 3. And the subscript of the unknown of the third equation is 4. So as you go down the equations, the subscript increases, which means if I have, say, A3 plus 3A5, and then A1 minus 2, okay, let me rewrite this in some. So if I have, say, A3 plus 3A5 equals to 7, and A1 minus 2A2 plus A5 equals negative 4, and A4 minus 2A5 equals 3. If you derive this equation, then that is not the final destination. Okay? Due to this third requirement, if you happen to have these two equations in this order, then we want to perform interchange operation to interchange the first and second equations so that you obtain the equations as in the system 4. Okay, so we want to transform the given problem into a form satisfying this. Okay, and the third one implies that means as you go down, the pivots will move to the right. So A1 was the pivot. In the second equation, A3 is the pivot. So if you go down, okay, thus in the second equation, the pivot is shifted to the right. And then if you go from the second equation to the third equation, in the third equation, A4 is the pivot. So if you go down the equation, the pivot is shifted to the right. So in the first equation, the first unknown, A1 was the unknown. And then in the second equation, the third unknown, A3 is the pivot. And then in the third equation, A4, the fourth equation, is the unknown. If you had more equations, then the same pattern should be repeated. If you go down, the pivots must be shifted to the right. Okay, so that's the form, that's the shape we want to derive in our simplified version of the equation, in the system of equations. Okay, so we want to have this. Okay, so in equation 5, in the system 5, the system 5 does not satisfy the requirements because, oops, oh, so in system 5, the system 5 does not satisfy this requirement because the coefficient of x5, x3 in the second equation is 2. So that's not what we want. Okay. In system 6, x3 appears in two equations, even though x3 is the first unknown in the second equation. And in the system 3, x4 is the first unknown in the second equation, but I mean x4 is the pivot, but sorry, not pivot, but so x4 has the x4 is the first unknown with the non-zero coefficient. In the third equation, x2 is the first unknown with non-zero coefficient. So as I said, if you go down, the these coefficients, okay, must be located to the right, and that is not satisfied in system 7. Okay, okay, so these non-zero coefficients, so as you go down, the non-zero coefficient, the first non-zero coefficients must be shifted to the right. And as I said, this first non-zero coefficient in each equation. So the first non-zero coefficient in each equation, that is called a pivot. So the statement 1 says in each equation, the pivot, the first non-zero coefficient in each equation, that coefficient must be 1. That means the pivot must be 1 in each equation. In okay, so and the third equation, the third requirement tells you that as you go down the row, the pivot must be shifted to the right. Okay, so that's what these two slides imply. And let us consider the following example too. So here we claim that this is a linear combination of these two polynomials. Okay, why is it so? So then how can I prove that? How can I, so I claim that the first polynomial 2x cubed minus 2x squared plus 12x minus 6 is a linear combination of these two equations. Then how can I prove this? If that the first equation, the first polynomial is a linear combination of the next two polynomials, then we need to prove this, we need to determine if two numbers, say C1 and C2, exist, satisfying such that C1 times x cubed minus 2x squared minus 5x minus 3 plus C2 times 3x cubed minus 5x squared minus 4x minus 9 equals the given polynomial. Then that means that means the sum of the coefficients on the left must match the corresponding coefficient of the polynomial on the right. So that means C1 plus 3C2 must be 2, and minus 2C1 minus 5C2 equals minus 2, and minus 5C1 minus 4C2 equals to 12, and minus 3C1 minus 9C2 equals minus 6. So you need to check, okay, please check if this system, even though you have only two unknowns with these four equations, this system will have a solution. So please check this yourself. It is not that difficult. You can just construct an augmented matrix, and then you can perform the elementary row operations to derive the echelon form, reduce the form, and you simplify the matrix to satisfy these three requirements, and then you can just identify the values of the unknowns. So that is not that difficult. But the one interesting claim is that the given polynomial is, but this polynomial is not a linear combination of these two polynomials. So to check this, let us consider the following. So if I consider the following equation, if this were a linear combination of these two polynomials, then there must be two coefficients a and b satisfying this equation. Then this system of four equations in two unknowns a and b must have a solution. Now, given this, if we perform the previous row operation to simplify the equations, then, I mean, if I eliminate a from the second up to fourth equations, then this is what you get. Okay, b equals to 4. Okay, that is fine. 11b equals to 22. That seems to be acceptable. I mean, the shape is acceptable. The problem is this one. That does not make any sense, right? 0 equals to 17. Then we have a contradiction, right? So A and B satisfying this equation do not exist. So that means this polynomial on the left is not a linear combination of the other two polynomials. Of course, when you look at the second and third equations, then actually we have another contradiction because the b in the second equation implies the value 4, while the third equation implies that equals to 2. So we have another contradiction. But anyway, one interesting contradiction is the fourth one. When I consider some manipulation, when I consider some row operations, at some point you have this 0 equals to some non-zero value. That means if I have the augmented matrix, this matrix is transformed to this. So here, the left two columns correspond to the coefficients, and the rightmost column represents the values on the right hand side of the equation, right? And after some calculation, some row operations, if some row becomes if some row becomes this shape, zeros in the coefficient area and some non-zero value on the right hand side area, then we have a problem. We get a contradiction. Okay, and in that case, there won't be any solution. So if in the middle of the calculation, if you see such row, so when I say such, if you see this shape of row, some zeros in the coefficient area and some non-zero value on the right hand side, then the system, the corresponding system does not have a solution, and you can stop there and you can just say the solution does not exist. Now, sup- suppose that S is a non-empty subset of a vector space. Okay, then the span of S represents the set of all the linear combinations of the vectors in S. Okay, so given S, given some set, okay, if you consider any linear combination, if you collect all the possible linear combinations, and then if you define that set, then that set will be called the span. Okay, and it, the symbol to denote the span is this. A span of S denotes the set of all linear combinations of the vectors in S. And then we define, okay, we define span of an empty set is the zero space. Okay, so this is what span of an empty set is. So please, so this is the definition. Okay, so we will define the span of an empty set with the zero space. And in R3 space, you can easily check that the span of 100 and 010 represents all the vectors on the xy plane, right? I mean, for any a and b, we can represent that AB0 vector as a linear combination of 100 and 010. So, so the span of 1, 0, 0 and 0, 1, 0 will be the points in the xy plane. If identity matrix is given, and if I use E1, E2, E3 to denote the columns of the identity matrix, then the span of E1, E2, E3 will be R3 space. And that will be the same as the span of 1, 0, 0, 1, 1, 0, and 1, 1, 1 vector. Please check this. Okay. So span of 1, 0, 0, 0, 1, 0, 0, 0, 1 will be the same as the span of with these three vectors, and both will define the R3 space. So please check this yourself. And span of any set of a vector space. So given V, if you consider any subset, okay, this subset, and then if you consider the span of that subset, it will be a subspace. And and any subspace of V that contains S must also contain the span of S. So let us check this. So if this S is an empty set, then the proof is trivial because we defined span of an empty set is the zero space. So that is a subspace of V, and any vector space contains a zero. So it is a subspace that contains S, and it is contained in any subspace of V. So now let us consider the case when S is not an empty set. So if S is not an empty set, then there must be some element in S. So S contains some vector, say Z. Okay. Then when I consider span, then I'm just considering all the possible linear combinations of Z. So that means when I multiply any number to Z, that product, that scalar multiple must be included in the span. So when I multiply 0, you obtain 0 vector. So span must include this 0 vector. So this 0 will be in the span, right? So now, suppose that I consider any two arbitrary elements. Now, in order for this span of S to be a subspace, I need to show that x plus y must be included in the span. And also, I must show that any scalar multiple of x must be included. So when I consider any arbitrary elements x and y in span, now what does that mean? X in span of S. That means X is a linear combination of some vector. So X is a linear combination of some elements in S. So when I choose some elements in S, X is a linear combination of those. And in a similar way, if Y is chosen from the span of S, then there must be some elements in S such that Y is a linear combination of those. Then when I add X and Y, you get the sum of these vectors. Now, since U1 up to UM and V1 up to Vn are all assumed to be vectors in S, this is a linear combination of the vectors in S. So this is in the span of S. In a similar way, if I multiply any number scalar to x, then you get this. And that is another linear combination of u1 up to um, which are included in S. So that is also, this C times X is also included in the span of S. So that means span of S will be a subspace. Okay. Now, suppose that W denotes any subspace of V that contains S. Okay. Now, to prove that the subspace, the span of S is included in W, so to prove, please remember that in elementary school days, given two sets, if I want to show that A is a subset of B, if when I choose for any X in A, if I can show that X belongs to B, then that will prove that A is a subset of B. So in order for this W contains the span of S, let me just choose any arbitrary element from the span of S, and then and then let me show that this W belongs to this W space. So if W is included in the span of S, then this W is a linear combination of some elements in S. Okay? So this here, W1 up to WK are some elements in S. Now, since S is included in W, W1 up to WK are some elements in W. So W, okay, which is a linear combination of these K vectors in W, will be included in W because W is a subspace. So that means any arbitrary element in the span of S belongs to W space. So that means the span of S will be included in the any arbitrary subspace of V containing S. So in other words, this span of S is the smallest in some sense, smallest subspace of V that contains S. So that's what we can tell. Okay. Just oh let me answer one question. So given the question was this: given some matrix, say 1, 2, 3, 4, 5, 6, 7, 8, 9, and or so given this matrix, then the question was, how do we identify whether this matrix A is the augmented matrix or just a coefficient matrix? Now, the size of the matrix does not tell you, okay, the size or the entries of the matrix does not tell you the answer. You need to understand, we need to understand, we need to identify from the context. Okay, so this A may be an augmented matrix or just a coefficient matrix. So if I just consider x plus 2, y equals 3, 4x plus 5, y equals 6, and 7x plus 8, y equals 9 problem, then this will A will be an augmented matrix. But if I consider x plus 2y plus 3z equals to say 0, 4x plus 5y plus 6z equals to 0, If I consider this problem, then in that case, A will be a coefficient matrix. So you need to understand the role of the matrix A from the context. Okay. So even though it is a 3 by 3, it may be a coefficient matrix or it may be an augmented matrix. And yeah, now a subset S of a vector space V generates V if span of S equals V. In this case, we also say that the vectors of S generate V. Okay, so what does the definition say? So here we have a vector space of V. If span of S equals V, okay, then we say this S generates or S spans the space V. Okay, now many students in the past do not understand the equality. Span of S and V, if they are equal, then we say S generates V space. Okay, so one example. Okay, I have some examples here. So you can prove, as I said, span of 1 0 0 0 1 0 0 0 1, which we commonly use E1, E2, E3. It is R3 space. So we say E1, E2, E3 generates R3 space, or we say E1, E2, E3 spans R3 space. And or you can say 1 0 0, 1 1 0, 1 1 1 also generates also R3. Or as in example 3, 1 1 0, 1 0 1, 0 1 1 generate R3. Now, how can I prove this? If I want to prove that they generate R3, I need to show that the span of these three vectors equals R3. Okay? Now, this 1 1 0, 1 0 1, 0 1 1 are vectors in R3. So, and from the previous theorem, span of 1 1 0, 1 0 1, and 0 1 1 is a subspace. This is a subspace of R3 space, right? So the previous theorem implies that this is a subspace of R3 space. Okay, that means this span, that span is a subset of R3 space. Now, okay, so in order for in order to show that two sets are equal, so the definition says span of S equals V, then that means span of S is a subset of V and V is a subset of span. If these two can be proved, then span of S and V will be equal, and in that case, S will generate V space, right? Now, in this example, the first part was easy because we just selected the three vectors from R3 space. So their span will be a subspace of R3 space. That was the claim in this theorem. So the first part is easy. And for the second part, in order for R3 is a subset to be a subspace, a subset of the span, we need to show that any arbitrary element in V belongs to the span of S. That's what we need to show. So in this example, we just selected an arbitrary element from R3 space. So we just selected an arbitrary element from R3 space. And then we want to show that that belongs to the span of those three vectors. To prove that, I need to prove the existence of three coefficients satisfying this problem, this equation, because the existence of R, S, and T will show that this arbitrary vector on the right is included in the span of those three vectors, right? Now, for this problem, you can easily find solutions. So that means this part means span of those three vectors, okay, that includes R3 space. And the previous theorem implies that this span is a subset of R3. So this part proves this, and this direction comes from the previous theorem. By combining these two, the span of those three vectors equals R3 space. This is how we prove that these three vectors generates R3 space. Now, in example 4, I have one, two, three problems, three polynomials. And okay, and the claim here is that they generate P2 space. Now, first of all, we just selected three vectors. So let me call the first one by, say, U vector, U, and the second polynomial by V, and the third one by W. Then please note that these three polynomials U, V, W are chosen from the beginning from this P2 space. Then the previous theorem implies the span of those three polynomials will be a subset, some subspace of P2R. Now, to prove the other direction, we just select an arbitrary polynomial, ax squared plus bx plus c, okay? And then we want to show that this arbitrary polynomial in P2 belongs to the span of UVW. In other words, we need to show that ax squared plus bx plus c can be written as a linear combination of those three polynomials UVW. And the example just shows one possible solution. So for these three coefficients, okay, these three polynomials will generate P2 space. And one more example. Given these three polynomials u, v, w, if I define any arbitrary polynomial, say y as, say, x squared, that is in P2, then since u, v, w generate an arbitrary polynomial in P2, when I consider span of u, v, w, and y, please note, first of all, that this span of these four polynomials will be a subset of P2R by the theorem we considered. So one direction is easy. Then how about the other direction? When I choose any arbitrary polynomial P2 in P2, say ax squared plus bx plus c, then the previous note, say minus 8a plus 5b plus 3c times u plus 4a minus 2b plus minus c times v plus minus a plus b plus c times w. And then I can add 0 times y, and that will be ax squared plus bx plus c. So that will prove the other direction. So by combining these two, I can say x, u, v, w, and y will generate P2 as well. Okay. And how about this? So if I consider four matrices, then their span will be, so the span of these four matrices will be a subspace of M sub 2 by 2 by the theorem. Now, if I choose any arbitrary element from M sub 2 by 2 space, then that can be generated as a linear combination of these four with those weights. So that means this portion implies that this M sub 2 by 2 is a subset or subspace of the span of those four matrices. So that means these four matrices will span M sub 2 by 2. Okay? So these four matrices will generate M sub 2 by 2 because of this. And please note that if you have only three matrices, you cannot generate all, I mean, you can generate some matrices in M sub 2 by 2, but not all of them. Okay? So those three are not sufficient. You can check. Okay? Now, before I go to the next part, let me consider some example. So here, um, okay, so suppose that we have three vectors u, v, w, and span of these three vectors equals, say, R3 space for some u, v, w vectors. Then the question, does that, oh, and and say V is a subspace of R3 space. So suppose that span of three vectors is R3 and that V is a subspace of R3. Then if I claim, here is my claim, some subset of this will span, if I claim this, some subset of three vectors will span the space V, then if I make this claim, is it true? Claim? Or is it forced? Can it be forced? Is it true for any UVW and any V space? Okay. How about a V is the span of, say, 1, 2, 3. And if U is 1, 0, 0, V is 0, 1, 0, and W is 0, 0, 1. In that case, when I consider the span of UVW, it will be the R3 space. It contains V space, but it is not the same as V. V is a proper subset of R3 space. So span of UVW cannot be V space. Okay. Now, if I consider any subset, say span of UV cannot contain 1, 2, 3 vector. So that means V is not a subset. So that means V is not included in the span of U and V. And span of U and W does not include that vector either. Span of V and W cannot include that 1, 2, 3 vector. Or if you consider span of U or span of V or span of W or even span of an empty set, none of these include 1, 2, 3 vector, right? So V cannot be included in any span, in the span of any subset. So this claim above may not be true, okay, in some case like this. So please be careful about the definition of the span of some set. Okay, the examples in the note are very straightforward, very simple. But if you consider some subspace, okay, and if you know some set generating this whole space, okay, may not generate this subspace. So please be careful about this example. And then let me go to the next section. Okay, now we want to consider this interesting concept. So we say, given a vector space, we say a subset S is linearly dependent, okay, if there exists some vectors, say u1 up to un, and some numbers, not all zero, such that the linear combination of these vectors in S produces 0 with those a1 up to an as the coefficients. Okay, so in that case, we say S is linearly dependent, or the vectors are linearly dependent. And at that point, this this equation is called linear dependence relation. So as an example, if I consider 1, 0, 0 vector and 2, 0, 0 vector, then when I multiply -2 to the first one, and then if I multiply 1 to the second one, if you add them, you get 0, 0, 0. So 1, 0, 0 and 2, 0, 0 are linearly dependent because they produce 0 vector. If I consider x squared plus 1 and -2x squared plus 1 and 1, when I multiply -2 to the first polynomial and then 1 to the second polynomial, and then if I just add 1, you get 0 polynomial. So here I multiply 1 to the 1. Okay. So that means these three polynomials, x squared plus 1, -2x squared plus 1, and constant function 1, they are linearly dependent. Minus 2 times x squared plus 1 plus 1 times -2x squared plus 1 plus 1 times 1 plus 0 times x squared will be also 0. So these four polynomials will be also linearly dependent. Okay. So we say the vectors are linearly dependent if you can produce zero vector with at least one non-zero coefficient, not all zero. That means some of them may be zero, okay, but not all zero. So with such coefficients, if we can produce zero vector, then we say these vectors are linearly dependent. Okay. Otherwise, so a subset of S of a vector space will be called linearly independent if those vectors are not dependent. So what does that mean then? What is the meaning of this? So when I consider, so if S consists of, say, u1 up to un vectors, okay? Now, if I consider a linear combination of those vectors, and then if this is a 0, if I assume that this linear combination is 0, and if those vectors are not linearly dependent, that what does that mean? That means the coefficients must be all 0. So if this equation implies that x1, x2 up to all xn, these coefficients are all 0. So if this is satisfied, then we say S is linearly independent. Okay. So in other words, the zero vector can be constructed as a linear combination of u1 up to un with only zero coefficients. If that's the case, then the vectors in S are said to be linearly independent. Okay, but but if if that's not the case, that means if any of the coefficients is non-zero, but if you can still produce zero vector with those n vectors in S, then we say those vectors in S are linearly dependent. Okay. Now, if I have linearly dependent vectors, so suppose that S consists of n vectors, and if that, let me assume that this is linearly dependent. Then that means some x1 up to xn exist, okay, such that x1 u1 up to xn un is 0, and at least one of the numbers in X is different from 0. So this vector of x1 up to xn is not the 0 vector. So that at least one of them is not 0. Okay? So at least one of the numbers in these n values is not 0. So say x1 is not 0. Then this equation, this linear dependence equation tells you that x1 u1 will be, if I move all the other terms to the right hand side, you get negative x2 u2, negative x3 u3, negative xn un is obtained. Now, what if I divide this equation by x1? I can perform the division by x1 because x1 is not 0. If x1 were 0, then I cannot divide the equation by 0. But since x1 is assumed to be non-zero, I can divide the expression with 0. Then what do we get? Then from the left, we get u1. That is negative x2 over x1 times u2, negative x3 over x1 times u3, and negative xn over x1 times un. What does that mean? That means u1 is a linear combination of u2 up to un, right? So what is the assumption here? If I assume that the set of n vectors is linearly dependent, then some vector will be a linear combination of the others, right? So that's the one conclusion. Now, what if I have the conclusion? So suppose that one vector, say v u1, is a linear combination of, say, u2 up to un. Then that means that means there exists some numbers x2 up to xn such that u1 can be written as x2 times u2 plus x3 times u3 plus xn times un. Now, if I move this u1 to the left-hand side, we get negative 1 times u1 plus x2 u2 plus xn un equals 0. So, what I get is some linear combination of u1 up to un producing 0 vector, and the coefficient of u1 is not 0. The coefficients of the other guys, okay, x2 up to xn, they may be zeros, but it doesn't matter. As long as the coefficient of u1 is not 0, then this relation, if you can produce a 0 vector from these n vectors with some non-zero coefficient, then this u1 up to un, the set of these n vectors will be linearly dependent. So if I assume that some vector is a linear combination of the other vectors, then the collection of these n vectors will be dependent. And previously, I considered the converse. When S of n vectors is linearly dependent, then some vector will be a linear combination of the other vectors. So in conclusion, we have the following. If S is linearly dependent, if and only if some vector in S can be written as a linear combination of the other vectors. So here I said some vector, not every vector. Okay. So for example, if I consider 1, 0, 0 and 0, 0, 0 vector, then 0 times 1, 0, 0 plus 1 times the 0, 0, 0 will produce the 0 vector. So that means the set of 1, 0, 0 and 0, 0, 0 will be linearly dependent. But this 1, 0, 0 is not a multiple of 0, 0, 0 vector, right? Of course, 0, 0, 0 is a multiple of 1, 0, 0 though. Okay, so some vector in the linearly dependent vectors is a multiple of the other vectors, but not every vector is a multiple of the other vectors. So that is a property, some property of linearly dependent vectors or linearly independent vectors. So given this set S with these four vectors in R4, okay, and when in order to check whether this S is linearly dependent or independent, to determine, you first put this equation. I mean, you need to put the linear combination of the given vectors is 0. You set this, okay? If A1 up to A4 are 0, must be zeros, then the vectors are independent. Otherwise, dependent. Okay, so then, so how can I solve this? Well, you need to derive an equivalent system of equations and construct an augmented matrix. So from this system, we derive a system of equations, and then we consider augmented matrix with coefficients and the values on the right, and then you perform elementary row operations to simplify the equations. You know what I mean? So, for example, you first construct the augmented matrix, and then you need to perform elementary row operations to eliminate 3 minus 4 and 2 in the first column. And then you go to the next column to eliminate the entries below the pivot and so on. Then for this particular problem, okay, for this problem, you can find many solutions. One example will be this. But that's not the only solution. You can plug in zeros, right? But that is not what we want. We want to find we want to check whether this problem has a non-trivial solution with some at least one non-zero value. Okay? So we have linear dependency relation. And as I said, in that case, at least one vector can be written as a linear combination of the other vectors. So, so the set S is linearly dependent. That's how we prove that. In example 2, we are considering three matrices in M sub 2 by 3. And this linear combination with these coefficients will produce the zero matrices. So that means these three matrices are linearly dependent. Then at least one of the matrices can be written as a linear combination of the others, right? So if I call A1, these guys as A1, A2, A3, then as you can see, 2A3 equals 5A1 plus 3A2. So A3 can be written as 5 half of A1 plus 3 half of A2. So we can represent at least one matrix in terms of the others. So empty set empty set is all we assume that okay, we assume that empty set is linearly independent, okay, and if one set consists of only single vector, okay, if the set consists of a single vector, if the vector u is 0, then the set will be dependent, otherwise independent. Okay. And as I said, if if a set, okay, so if your set consists of a single vector, then if the vector is 0, dependent, non-zero, independent. If I have two vectors, it is dependent if and only if u is a multiple of v, or v is a multiple of u, then this set is dependent and vice versa. Otherwise, independent. So it is independent. V is not a multiple of u, and u is not a multiple of v. In that case, the set of two vectors will be independent. So, as an example, if I consider 1, 0, 0 and 2, 0, 0, which we considered as 200 is a multiple of 100 vector, so the set is linearly dependent. But if I consider 100 and 110, then so this is dependent, but this is independent because 100 is not a multiple of 110 and 110 is not a multiple of 100. So if you have two vectors, then it is very simple. If one is a multiple of the other, then the set is dependent, otherwise independent. I can extend this to a set of many vectors. Okay, so set is linearly independent if and only if the zero vector can be produced with as a linear combination of the given vectors with only zero coefficients. So trivial representation means zero coefficients. So given vectors, if you can produce only zero coefficients, then the set will be independent. Otherwise, dependent. And and this is this some extension of the second property, or S of several vectors u1 up to un is dependent if and only if some uj is a linear combination of the others. Even though this property is a little bit difficult to apply because if you have many vectors, then it is not that clear. But if you have only two vectors, then it can be easily conformed. So it is very easy to use this property to check the dependence, linear dependence of the set of two vectors. Okay, and yeah, so equation 3, example 3 to prove. Yeah. So in order to prove that this set is linearly independent, then then you need to consider this equation. The linear combination of the given vectors is said to be zero. And then if you can show that the solution is the trivial solution, I mean, trivial solution is the only solution for this problem, then the given vectors will be linearly independent. So then the only solution to this problem is zero vectors. So in that case, these vectors will be independent. Okay, instead of example 4, since I don't have much time today, please consider the following example. The following. Given an M by M matrix A, okay, I consider it a pivot column and non-pivot column, right? So the set of the first claim, the set of pivot columns is linearly independent. Okay. So for example, okay, you can check this, right? And second, any non-pivot column can be written as a linear combination of preceding pivot columns. Okay, so please check, okay, these two properties. Okay, and then let me explain in more detail next time. Okay, thank you for listening and see you next time.